All right, a little bit about luminosity. It's one of the more important stellar parameters that we measure or calculate for a star. Here's how it works. Remember, luminosity is the amount of energy released. Really, it's energy released per second. But anyway, this is the absolute brightness, and what we've been saying is it's like the wattage. In fact, it's measured in watts, like the wattage of a light bulb, right? What's nice is that it turns out stars are really simple objects at a basic level, because the luminosity of a star only depends on two things. L depends on two things. It's really easy. The luminosity is just equal to R squared. This is the size of the star, the physical size, right? The radius. All these stars are pretty much spheres. So this is just the radius. You square it. And the temperature. In kelvins, we said that was basically Celsius. So luminosity is really R squared T to the fourth. It only depends. Oh my goodness, that's terrible. Let me make a nicer box. Luminosity only depends on the size of the star and its temperature. That's it. That's all you need to know. And yet, then you could calculate how much energy the thing radiates. It's just really pretty much basic physics. I mean, you got to square it and raise it to the fourth power, but that's just calculated work. This formula works if these are in what's called solar units. And for solar units, what we do is usually we put a little circle with a dot in it. That just means relative to the sun. So, for example, something that is, if T solar is 6,000 kelvins, for right now I'll use that. That's the temperature of the sun. That circle with the dot in it always means the sun's quantity. So if that's the temperature of the sun, then a star with T of 12,000, well, that would be twice as hot as the sun, right? So that would be 2 T solar. See, so all you do is you just divide whatever the absolute number is by the solar one, and then you get the thing in terms of solar. So if something is 3 times bigger than the sun, then our solar would be 3. Okay, and if you do that, then you can compute L solar, the amount that the star is brighter or dimmer than the sun in solar units. Okay, for example, let's do a quick example. So if a star has T of 12,000 kelvins, and suppose its radius is twice the sun, whatever the heck the sun's radius is. Suppose this is twice as big as the sun. How much energy does it put out? How much brighter is it than the sun? The luminosity in solar units is R squared T to the fourth, right? So you just do 2 squared. And if it's 12,000, this is 2 T sun. So this would be 2 to the fourth. So what the heck? 2 to the fourth. If you do that in a calculator, you get 16. And then multiplied by another 4, so that would be 64. So it's 64 times brighter in the absolute sense than the sun. So it puts out 64 times as much energy as the sun. That's a lot. So, and that's only for a star 12,000 degrees. So that would be like an A, B kind of star, and a star that's 2 times bigger. So if it's just twice as hot and twice as big, it doesn't produce twice as much energy as the sun. It shines with 64 suns, right? So it scales up really, really fast. This is how it works. Now, practically, we tend to do this. Watch this. L equals r squared to the 4th becomes, okay, usually what is the thing that we don't know? Okay, T is easy. You guys have done this. All you do is you look at the spectrum of a star and you can get its temperature pretty easy from Wien's law or whatever. That's pretty easy. So that's usually known. The luminosity usually we can get that from the distance, right? Because if we know how bright a star looks, we always know that. We can just measure how much light we're getting from the star. So if we know how bright the star looks and we know the distance, we can calculate the luminosity because we just adjust for that distance, because light falls off as 1 over the square of the distance. So anyway, all I'm saying is if we know the distance to the star, and for a lot of stars in the solar neighborhood, we know the distance, we can calculate L. So for most stars that we see that are fairly close by, we know the T and we know the L. What we don't know is how big they are, because all stars through a telescope just look like a point. They're so far away that we can't really resolve the disks very well. So calculating R is sort of an important thing. We'd like to know how big these stars are. So if we know L and we know T, we can solve for R. We just do a little bit of algebra. So this means, if I do a little bit of algebra, R squared is just equal to L over T to the 4th. And then probably you know if I want to solve for R, I take the square root of both sides. So R is just L, the square root of L over T to the 4th. So this is something that we use fairly often to figure out how large the star is. Here's an example. The red star Betelgeuse in Orion. It's a red supergiant. We'll talk about it next week or the week after. Anyway, we'll talk about it more in detail. It's easy to find out the temperature of the star. The temperature of the star, the temperature of Betelgeuse is about 3,500 K. It's a red supergiant. And we also know how far away it is, and we know how bright it looks. So we can calculate that its luminosity is 100,000 times the luminosity of the sun. It's a pretty incredible star. It puts out 100,000 times as much energy as the sun does. Okay, so first of all, in order to figure out how large this star is, let's put 3,500 in solar terms. So this is 3,500 we just divide by 3,500 divided by, I'm going to be a little bit more precise. The sun's temperature is 6,000. Yeah, it's really 5,800, so I was kind of rounding earlier. And so that is about 0.6 T solar. So let's put that in. Let's see. So Betelgeuse's radius is going to be 100,000 divided by, and then I'm going to take 0.6 to the 4th power. And if you do that, if you stick all that into your calculator, what you get is about 880 times the size of the sun. It's enormous. That's why we call it a supergiant. If you swapped out the sun and put Betelgeuse in its place, we would be right in the middle of it. We'd be inside of it. In fact, it would extend almost out. Let's see, 880. It would extend almost out to the orbit of Saturn. Even Jupiter would be inside of it. It's a gargantuan star. But this is how we find that out, because even Betelgeuse just looks like a point in most telescopes. So we have to calculate the size. So it's just a fantastically large object. To make sense of all this, a lot of times in science what we do is make plots. So one really convenient plot, I'll just draw it on this page, is called an HR diagram. We'll use it a little bit more as we go along, but I just want to introduce it. Oops. Here's the idea. When you put things on a plot like this, you have to pick two quantities. The book points out we could do the same thing for people. We could plot their weight and their height. And it turns out that most people fall along a band where the taller the person, the more they weigh. That's just sort of generally true. For stars, here's what we can do. I can plot the luminosity, I can plot the brightness, and I can plot the temperature down here. And the convention is that the temperature increases this way. That's a little bit backwards. Usually, when you plot things on an x-axis, the numbers get bigger as you go to the right. But the reason that we do this convention is because then I can write down things like this. I can do O, B, I'll just put them in different colors just for fun. A, F, G, K, M. Yeah, the reason we plot it like this is because then the spectral sequence is the usual run of letters. O, B, A, F, G, K, M. Those are the spectral types. Written down from hottest to coldest. That's usually the way we like to write them down. So that means that the temperature increases to the left, right? Because the O's are hot and the M's are cold. Anyway, if you do this, if you plot a whole bunch of stars on this diagram, if you take sort of a scoop out of a galaxy and you plot these stars on a diagram, what you end up with is roughly, you get a band of stars. Then this band is called the main sequence. About 90% of all stars are right there on the main sequence. And if you look at the plot, all this is really telling you is that cool stars, like M's, generally are not very luminous. They don't emit much energy. You kind of already knew that because L is R squared T to the fourth, right? So if the temperature is low, then L is probably going to be low. There's a group of stars, though, that are up here. If you plot a bunch of stars together, there's a group that ends up there. And think about that for a minute. What does that mean? Those are stars that are cool. They're K's and M's. So the T is low. But the luminosity is high. So what's the only way, if the T is low, what's the only way that the L could be high? The only way that that could happen is if the radius is really high, right? These are giants. Those are called giants. Some stars can be giants. It's sort of like fires. What's the only way that a cool fire could be seen a long way away, could be really luminous? Well, if it's really big. So things that are cool can emit a lot of energy if they're really large. Those are the giants. And then we also find, so this is maybe 5% of stars are in there somewhere. And then another 5%-ish that we can see are down here. Think about that group.
What's true about that group? That group, let me erase those. That group
is hot, right? Those are A's and B's.
B's. So that group has a high temperature.
But the luminosity is really low. They're dim.
Right? They don't put much. They don't
emit much energy. What's the only way that T could be really large and yet L is really small?
That's if R is small.
These stars are tiny. They're dwarfs. Not dwarves with a V. It's dwarfs with an F. So that's another 5% or so. And so when you first see this, when you first see this diagram, it's a little bit of a puzzle. Most stars, the sun, for example, the sun is right there in the middle of the main sequence. It's a G-type star, and its temperature and its luminosity pretty much correlate right with all the other stars, lies right in that band. So why are some stars dwarfs and some stars giants? You could imagine different possibilities. Maybe some stars are born giants and they stay giants, and maybe stars are born dwarfs.
Maybe it goes like this. Maybe stars are born dwarfs
and they move into the main sequence and then they end up giants. That's possible.
Or maybe giants are really young stars, and as time goes on,
they sort of contract onto the main sequence and then become dwarfs. Or maybe none of that happens. Maybe they just stay wherever they are. So this is sort of a puzzle. Why are some stars giants? Why are some stars dwarfs? But most of them are on this band, this main sequence. That's a puzzle that we're going to get to starting with the next unit on stellar evolution. But anyway, this is just how we plot the way the stars look as they are right now. So we're not saying anything about one's kind of star moving into a different type of star. All we're saying is that when we plot them, this is sort of the picture that we come up with. And by looking at the diagram, you can tell right away which stars are large and which stars are small.
Generally,
the size of the star, the radius of the star goes up as you go to the upper right part of the diagram because you're getting cooler and yet more luminous. So that means that the size is getting larger. Okay, more on this next week.